In this video, we are going to do an estimating instantaneous rate of change example. So IROC, remember, it stands for instantaneous rate of change. So the example is the following. Let d of t be the number of people in Disneyland t hours after it opens at 8 a.m. given in this table. Suppose that it closes at midnight. Okay, so this table gives me a row that keeps track of t, which is the number of hours after it opens, and d of t represents the number of people, and it says here in the table that these values are in thousands of people. So this 12, for example, at t equals 2, means there's 12,000 people in the park 2 hours after it opens. So the question is, I want to estimate the instantaneous rate of change of d of t, so of my function, at noon, and be sure to state the units. Okay, so I want to estimate the instantaneous rate of change. Okay, so the first thing I want to observe is it's talking about noon. Well, what time is this? This is t equals, so noon is how many hours after it opens. It opens at 8 a.m. Well, this would be 4 hours after it opens. So this is actually t equals 4, not t equals 12. So we want to be careful about that. We need to remember what t represents. Okay, so this is talking about finding the instantaneous rate of change. We saw at the end of the last video that we had a formula for the instantaneous rate of change that involved a limit. But in this problem, I don't have a formula for my function. So I won't be able to determine the instantaneous rate of change exactly. The best I can do is we can estimate the instantaneous rate of change, IROC, with an average rate of change. Okay, so there are a few options I'm going to present to you, and I want to pose this question to you all, and that is, which of the following would be best? Okay, so I'm going to write down 3 average rate of change. So first, the average rate of change over the interval from 2 to 4. B, the average rate of change over the interval from 4 to 6. Or C, the average rate of change over the interval from 2 to 6. Okay, so 3 options. At this point, pause the video for about 1 minute and see if you can determine which one seems to be best. 4, 3, 2, 1, pause the video. Pause the video for about a minute and really think about which one of these seems like it would be the best option. Alright, so hopefully you've done that. Hopefully you've paused the video for about a minute to think about this. So I'm going to say that the best option is C, the average rate of change over the interval from 2 to 6. So why? Why am I picking C? So the thing about C is this incorporates both sides of the number that we're sort of interested in, which is t equals 4, both sides of 4, which in general is good. Like if something extreme is happening on one side of 4, but not on the other side of 4, taking the average rate of change over the whole interval that sort of spans both sides of 4 is good, because it's going to take both of those into consideration. Okay. So all of these, A, B, and C, they would all give me estimates. I just think for this reason that C would give me the best estimate. Okay, so let's determine this. So we want to know we're trying to estimate the instantaneous rate of change at t equals 4. And we're going to estimate and say that, that's approximately going to be the average rate of change over the interval from 2 to 6. From 2 to 6, oops, that should be a closed bracket there on the 6. Okay, so let's use our formula for average rate of change. So it's the slope formula. It's going to be d of 6 minus d of 2. That's the change in y on top, and change in x on the bottom. So 6 minus 2. Or I guess in this case, technically it's change in t on the bottom, because my variable is t. And, well, what's d of 6? I have to go back up to my table. Let's zoom it out a little bit. D of 6 is 25, D of 2 is 12, and on the bottom we have 4. So we have 13 over 4, which as a decimal is 3.25. So that is our average rate of change, which is going to be our estimate for the instantaneous rate of change. But the problem said also to state the units. So what are the units for this this average rate of change, our estimate here? Well, it's the change in whatever the variable d is over time. So d is being measured in thousands of people. So it's thousands of people on top. And what was t measured in? Hours. So it's 3.25 thousands of people per hour. And that is our estimate. Okay, so what does this number tell us? So this number means that at t equals 4, which is noon, the number of people in Disneyland is changing by this quantity, and that's our approximation. So the fact that this is a positive number means that the number of people in Disneyland is going up. So I can say that it's increasing because this is a positive number. So it's increasing by about, and I'm saying about because it's an estimate, about 3.25 thousand people per hour. So we sort of approximate that from t equals 4 to t equals 5, an extra 3.25 thousand people would enter the park. Of course, that's not exactly right, or it may not be exactly right, because this is just an estimate. Alrighty. But looking at our table, that does seem to make sort of intuitive sense that I should get a positive value, because looking at what happens from 4 to 6, we see that the number of people in the park did increase. It went from 20 to 25, so it did increase. So it does make sense that we should expect a positive value like this. Alrighty. Now, another reason why we should expect a positive value is it also increased on the interval from 2 to 4. The number of people increased from 12,000 to 20,000. Okay. So at this point, let us just recap what we've talked about with these rates of change. So I'm going to make a little table here to sort of recap. So we have these two quantities, average rate of change and instantaneous rate of change. And for each of them, let's list their formula. So let me say the average rate of change of f at, this should be over an interval. Average rate of change of f over an interval from a to b. An instantaneous rate of change, this is of a function, let's say at x equals a. So what are their respective formulas? So for average rate of change, it's the change in y, f of b minus f of a, over b minus a. That was a formula for average rate of change. And for instantaneous rate of change, it was a limit as h approaches 0 of f of a plus h minus f of a all over h. So that was the formula for instantaneous rate of change. And then I want to keep track of, well, what does it represent? What does it represent? So for average rate of change, f of b minus f of a over b minus a, this was the slope of the secant line. And for instantaneous rate of change, this was the slope of the tangent line. Okay, so let's really make this into a table. Let's separate out these two rows. Okay, and then I have this row of labels on the top. Okay, so we have these formulas for both of these quantities. We've written down what they represent. And let me also just make a note of, we have this other definition for what we're going to call this slope of the tangent line, this limit, this instantaneous rate of change. So the slope of the tangent line, and I should say the slope of the tangent line to the function at x equals a. And even for the slope of the secant line, between the points a comma f of a and b comma f of b. And what I was about to say before was the slope of the tangent line to our function at x equals a. We call this the derivative of f at x equals a. And we'll talk about that more in the next section. Okay, so let's box this.